Every product failure in series production is traceable back to a misunderstood or unvalidated requirement. It never starts in PPAP. It never starts at SOP. It always starts when a project team accepts ambiguous customer language as engineering truth. This lecture will change how you think about requirements forever. Let's start by correcting a very common misunderstanding. Most engineers think voice of the customer, or VOC, simply means whatever the customer wrote in the RFQ. That assumption is dangerously wrong. In Automotive APQP, VOC is not a single document. It is the sum of all expressed and implied expectations coming from multiple sources, many of which are incomplete, inconsistent, or even contradictory. Your job in APQP is not to receive VOC. Your job is to extract, interpret, and close the gaps. In reality, VOC is scattered. You'll hear it in the RFQ technical package, where the customer might mention IP protection, lifetime, or environmental exposure, but usually without defining test methods or acceptance criteria. That vagueness is your first hidden risk. Then you move to customer drawings. These give you envelope dimensions and interface geometry, but very often they stop short of specifying tolerances, surface roughness, or flatness requirements. Those missing details will come back later as quality problems. Next are customer-specific requirements, or CSRS. These often dictate how DFMEA must be structured, or how deep PPAP submission should go. The danger here is that CSRs are not always synchronized with your APQP timing. Some of the most valuable VOC comes from field failure history, past leaks, corrosion issues, or EMC complaints. Unfortunately, this information is rarely shared formally unless you ask for it. You also have VOC coming from the regulatory environment, chemical restrictions, recycling rules, or marking requirements. The problem is that ownership for these requirements is often unclear. Is it design, quality, or compliance? Manufacturing also contributes VOC through the production concept, volume, ramp-up plans, takt time, and capacity assumptions. These are frequently misaligned with the depth of validation testing. Finally, there are warranty and PPM targets. Customers often set aggressive numbers without aligning them to design robustness or process capability. VOC is not missing. It's fragmented. This fragmentation is not accidental. It's structural. Customers focus on vehicle-level optimization. Suppliers carry the burden of component-level reliability. So when a customer asks for IP67, they're not thinking about leak rate physics. You are. When they say engine bay capable, they don't define thermal shock profiles. You must. When they demand EMC stability, they don't design grounding continuity through coatings. That's on you. If you accept VOC as complete, you accept responsibility for every undefined assumption. And those assumptions eventually turn into failures. To prevent chaos, VOC must be classified. Some VOC is functional, sealing performance, grounding paths, connector retention. Some is environmental, temperature ranges, vibration loads, chemical exposure. Other VOC is structural, dealing with stiffness, load paths, or flatness requirements. You'll also see process-driven VOC, which comes from casting limitations, machining tolerances, or coating processes. Then there's quality and reliability VOC, lifetime expectations, warranty limits, and allowable PPM. Manufacturing contributes VOC related to volume, takt time, and scrap tolerance. Compliance covers legal, environmental, and material regulations. And finally, logistics and service introduce requirements for packaging, labeling, and traceability. If you don't classify VOC, you'll either over-design the wrong things or under-design the critical ones. Let's look at typical VOC language. When a customer says, "the housing must be sealed," that statement is meaningless from an engineering perspective. There's no IP class, no aging condition, no pressure, no test method. Must survive harsh environment sounds serious, but without temperature, vibration, or chemical profiles, it's just marketing language. High EMC performance required gives you no grounding resistance, no test setup, no frequency range. Must be lightweight, has no mass target. Durability must match vehicle life, has no failure definition. Raw VOC is a starting point, not an input. This is why the VOC capture log exists. This document is not optional. It is your legal and technical firewall. Every VOC statement must be logged, categorized, and challenged. For each VOC, you document where it came from, how it was stated, and what is missing. You assign a customer owner to clarify expectations and a supplier owner to translate them into engineering terms. You define a due date and track status. If a requirement is not in the VOC log, it is invisible. If it is invisible, it will not be managed. VOC is qualitative. Engineering is quantitative. Every requirement must be testable. Every requirement must have a clear acceptance criterion. Every requirement must have a responsible owner. So, must be sealed becomes a defined IP class, verified after thermal cycling with a maximum leak rate. Must survive engine bay becomes operating and storage temperature limits. No EMC issues becomes a measurable grounding resistance after corrosion aging. If you cannot verify it, it is not a requirement. Another common mistake is treating all requirements the same. Some requirements are mandatory, legal or contractual, and failure is unacceptable. Others define performance, meaning they reflect customer expectations. Some exist for robustness, providing margin against variation. Others protect manufacturing feasibility, and some ensure regulatory compliance. Classifying requirements helps you spend engineering effort where it matters most. This is where most APQP projects fail. They stop at the first line. Take the simple requirement. The housing must be sealed. That single sentence actually hides multiple technical conditions. You need a defined gasket compression window to absorb torque variation. You need flatness limits to prevent microleaks. You need porosity controls to avoid leak paths. You need aging stability to prevent compression set. And you need a defined assembly torque window to avoid over or under compression. Most APQP failures happen because teams stop at the first sentence and never decompose it. Finally, everything must be traceable. That's why we need the RTM, the Requirements Traceability Matrix. Every requirement must link to a verification method, an acceptance criterion, a design feature, a DFMEA failure mode, objective test evidence, and a responsible owner. This traceability ensures nothing is assumed, nothing is forgotten, and nothing is debated at SOP. Let me leave you with this thought. If you cannot trace a requirement from the customer's voice to a design feature, to a failure mode, to a test, and finally to objective evidence, then your APQP may look good on paper, but it is not real, and reality always shows up after SOP.